Hi, welcome to Math 150, Section 2. We'll call it Lecture 28, 2021. This is one of the review classes. We're trying to wrap up the semester. And what I want to do today is, there was a question about talking about the different convergence tests. When do you use each one? And to some extent, the answer depends on how much experience you have. I am pretty sure I am more than twice the age of anybody who is taking this class. I have been doing these problems longer than you've been alive. For me, the comparison test is actually not so bad because I've been doing it so long, I just know so many different examples of things to try. And so for me, the comparison test is actually probably the easiest one to use because I just have so much experience. And so to me, I love the comparison test. Ratio, root, integral are more straightforward, more mechanical. Again, the example I like to give is looking at a quadratic, and can you just sniff out the roots and factor it, or do you have to resort to the quadratic formula? What's nice is the quadratic formula is mechanical. You turn the crank, it generates the roots. Ratio and root are very similar to that. We also have the integral test, and most of the time, the way the integral test works is you just replace n with x, and that gives you your function. It's worth saying before we do any of these big tests, always try to do simple things first. So the simplest thing is before we try any of these more elaborate tests to see whether or not the sum converges, we're looking at the sum n goes from 0 to infinity of an, check to see if the terms an go to 0. If the terms aren't going to 0, then there's no way the sum can converge, and there's no reason to bother using any of these. So frequently, the simplest thing to do is to just use does an go to 0. If it does go to 0, it may or may not converge. 1 over n diverges, 1 over n squared converges. So it's not enough to know that the terms go to 0. The last is our favorite New England transcendentalist, Henry David Thoreau, simplify, simplify. Before you do any algebra, before you do any problem, pause and see, is there a better way to do it? So after you take a class with me, one of your Pavlovian responses should be, whenever you see a product, take a logarithm. As I remark, if you are teaching third graders how to multiply, then resist the temptation. But when you're doing theoretical math or physics or arguments like this, you want to ask yourself, is it worth taking a logarithm? Is there a better way to write it? For the ratio test, we look at the limit as n goes to infinity of an plus 1 over an. For the root test, we look at the limit as n goes to infinity of an to the 1 over n. And so when we're looking at an to the 1 over n, sometimes it's easy to calculate the nth root by taking logs. And what's nice is we saw that the logarithm is a nice function. So if two numbers have an ordering, their log has the same order. Another way of saying things is, if I have a quantity that I want to study, it might be easy to study its logarithm. So imagine the logarithm goes to 5. Well, if the logarithm goes to 5, what does the quantity have to go to? So the natural logarithm of my quantity is approaching 5. What does the original quantity have to approach? e to the 5. If my quantity is approaching -1, when I take the logarithm, so the log of my quantity is going to -1, what does the quantity have to be going to? E to the -1. So rather than studying the original quantity, it's often easier to study the logarithm. So if I want to take the nth root, rather than looking at the limit of an to the 1 over n, it might be easier to look at the limit as n goes to infinity of the log of this, which would be the log of an divided by n. And that might just be an easier calculation to do. All right, so what I want to do is I want to do a problem, and we will go through for this problem all the different tests we can do and show how to do each one. I will probably say that for me, I prefer doing it by the comparison, and I'll do 2 different ways of doing it with the comparison test. But we will see that the other tests work well. So let's say we have the sum n goes from 0 to infinity of n to the 8 e to the -n. And again, when we're doing these analyses, we don't have to start the sum at 0. All we care about is what's going on from some point on. So instead of over here, we have infinity, 0 to infinity, I can erase that 0. And I only care about what's happening from some point on. And this is useful if you want to use the comparison test sometimes, because you may not have that it's always less than or equal to a series that converge. It might only be less than the series that converges from some point on. Well, if there are 6 terms where they disagree, doesn't really matter. That's not going to affect whether or not the sum is finite or infinite. It's not going to affect whether or not it converges. So we want to look at the sum of n to the 8 e to the minus 9. What makes you think that the sum might converge? What makes you think the sum might diverge? When you look at this, what could be a reason why it might diverge?
The n to the 8.
Yeah, we have an n to the 8. Why might it converge?
Negative
Yeah, the negative n. So it has 2 competing factors. And it turns out exponential decay kills polynomial growth. This is going to converge easily. There's a lot of different ways we can do the calculation. Instead of doing n to the 8, I could, of course, do n to any power. I'm doing 8 just for simplicity. Okay. So let's do a comparison. And again, this is years of experience. This is the same as looking at, n to the 8, e to the n in the denominator. I want to find a series whose terms are larger than this term by term by term. So n to the 8 over e to the n. I have to think, what do I know that looks like this that converges? Well, one thing is that maybe a geometric series, because I've got an e to the n that's looking like a geometric series. Maybe a p series, because I have an n to the 8. Well, for p series to converge, this is the sum of 1 over n to the p. It converges if p is greater than 1, diverges if p is less than or equal to 1. So I want this to converge with a p series. I want to somehow get this to be like less than 1 over n squared. Okay, well, let's see. If I look at e to the x, this is 1 plus x squared over 2 factorial, yada, 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 x to the 8 over 8 factorial, x to the 9 over 9 factorial, x to the 10 over 10 factorial, and so on and so on and so on. Well, if I look at e to the n, this is going to be greater than or equal to n to the 10th over 10 factorial. And the reason is I can drop all the terms but 1, and since it's a positive number, if I drop the terms, I'm just making it smaller. And the reason is I have e in the denominator, so if I make the denominator smaller, I make the fraction larger. This is where, again, it helps to have over 2 decades of experience doing these problems to just know what to compare it to. This is almost the method of divine inspiration, when you write down the right thing. The more problems you do, the easier it's going to be to see that this is something worth doing. Oh, I can cross multiply, and this is the same as 1 over e to the n is less than or equal to 10 factorial over n to the 10th. So this gives me that e to the n, or 1 over e to the n, is at most a multiple over n to the 10th. So n to the 8 over e to the n is going to be less than or equal to n to the 8 times 10 factorial over n to the 10. Oh, well, that's just 10 factorial over n squared. Yes.
Why did you choose 10? Was that just like
years of experience? And so I'm thinking in my mind, I want to do a p series.
okay.
I want to do a p series. So if I have an n to the 8, I have to be dividing by something a little bit more than n to the 9. Because if I chose n to the 9th, I would have a 1 over n, that's the harmonic series that diverges. I want to put something into the denominator that's at least a multiple of n to the 10. Because then that's going to give me a 1 over n squared. And this is where the comparison test is either easy or hard. The more problems you've done, the easier it is to just quickly look at it and see what you should be doing. And so here, the 10 factorial doesn't really matter. If I have a series that converges, if I multiply by 10 factorial, if I divide by 10 factorial, it doesn't affect whether or not it converges. This is 10 factorial over n squared. So I can compare to 1 over n squared, or which converges. So it's a p series, p equals 2. So we know the sum of 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. So I am just doing a comparison test. And so I know n to the 8 over e to the n is less than or equal to 10 factorial over n squared. So I can just compare it to a multiple of 1 over n squared. And this will give me convergence. The key is you have to see that when I have e to the n, e to the n is decay, e to the n is growing faster than any polynomial. So that's why I stopped and focused on this one over here. Is I focused on 2 more than x to the 8. So that I'll have a 1 over n squared. If I gave you n to the 15, what do you think I would use instead? What's challenge? X to the 17. If I gave you n to the 16.9, what would you use? X to the 18 would work, or the 19 would work to be safe. There's more than one choice you can make. Any questions on the comparison test for this? So this is the first way to do this problem with the comparison test. This is not the only comparison you can do. So let's see another comparison. Throw away all of this stuff. So we have n to the 8. This is the same as e to the log of n to the 8th power, which is e to the 8 log n. So I'm trying to get everything in some sense. This is very similar to the common denominator. I have an e to the minus n, I have an e to the 8. I want to write everything as an exponential of something. Okay, I can write everything as an exponential, and now I would get n to the 8 e to the minus n is going to be e to the negative n minus 8 log n. So when you just do the algebra and combine everything, negative is going to be positive. And again, this is where the more years experience you have, the easier it is to see that this is a good way to do the algebra. The idea is, this is going to show us that the exponential death is going to kill the polynomial growth. When n is really, really large, 8 log n is minuscule relative to n. What is the natural log of e to the 100? 100. So if I take n equals e to the 100, or the closest integer to that, this is e to the 100th power minus 100. That's essentially e to the 100. The minus 8 log n is minuscule. So Bill and Melinda Gates are in the news right now, and hopefully for them everything will be nice and calm. If one of them finds that they have a $20 bill that was stashed somewhere, do you think this is going to be a source of a fight in terms of who gets it? No, the $20 is going to be dwarfed by the other quantities here. The 8 log n is insignificant relative to the n. Let's make this a little bit more specific. N minus 8 log n is greater than 1/2 n if n is big. Do we agree with that? But once n is large, n minus 8 log n is so close to n that it's going to be at least 1/2. Well, then if we take the negative, we reverse the negative n minus 8 log n would be less than negative 1/2 n. And then that means e to the negative n minus 8 log n is less than e to the negative 1/2 n, which is 1 over the square root of e to the n. Because e to the negative 1/2 n is just e to the negative 1/2 to the n. So using e to the negative 1/2 n is e to the negative n is 1 over e to the 1/2 is 1 over square root of e. Okay, so now we know n to the 8 over e to the n is less than or equal to 1 over the square root of e to the n. What comparison test do I use? Compare to a geometric series. So when you do a geometric series, you have to tell me which geometric series. You have to tell me what is R. So what is R for this geometric series? 1 over the square root of e. And that is less than 1. So it converges. Is it surprising that we get convergence? No, we already showed a convergence. You should not be getting convergence with some tests and divergence with others. When you're doing these, you may initially try one approach, and then you might find that the algebra is getting painful. And if the algebra is getting painful, what should you do? Try a different one. And so what you do is you take your notes and you put them off to the side and you try another one. And if that doesn't work, then you try another one, then you try another one. And if none of them are working, then you circle back to the first one and you try that again. So don't throw away your notes, but if things are not working, try another test and see if it works better. Yes?
Could you do like, so you have n to the 8 over e to the n, and then could you like put that to the n and then do like n to the 8 over n and then e to the first?
So how do you want to do it into the 8 over?
8 over n. Like, sorry.
So how do you want to write it?
N, and then to the exponent 8 over n. And then over e.
Oh, I
and then put all that to the n.
and
then
do that to the end.
As n gets big,
So
that would
good.
just get tiny.
So this is excellent. So this is another way to do this with the comparison test. And what you would need to say is that n to the 8 over n is eventually less than, say, strictly less than e. And because we know n to the 8 over n goes to 1, eventually this is less than 2. This is less than 2 over e to the n in geometry. So yes, that would be a great comparison test to do. And in fact, that would be a better comparison test than this one. It's a little bit easier, a little bit cleaner. But you now have to use the fact that n to the 8 over n goes to 1. So eventually it's less than 2. But we know that. And so using that, that would be a faster comparison test. There are a tremendous number of ways of doing this. One of the things you often want to think about is what's going to give you the best rate of convergence, but if you're just trying to find if the sum converges, doesn't really matter. Okay, so lots of ways to do this with comparison. What should we try next? Ratio. And so we will try it with the ratio test. And after the ratio, and then to do the clean sweep, we will then enter the integral. So for the ratio, I always like to start by writing the limit as n goes to infinity of an plus 1 over an, so it's clear what we're studying. All right, so that's going to be the limit as n goes to infinity of an plus 1, so it's going to be n plus 1 to the 8 e to the negative n plus 1 divided by n to the 8 e to the negative n. So this is the limit as n goes to infinity of n plus 1 over n to the 8, e to the negative n, e to the negative 1 over e to the negative n. Okay, so the e to the negative n is cancelled. What is n plus 1 over n? What does that go to as n goes to infinity? 1. So if I raise it to the 8th power, what should it go to? 1. If something's approaching 1, if you raise it to the 8th power, it still goes to 1. If I replace 8 with n, this would actually go into e. This would be 1 to the n. It would just be the definition of e. It's very important that this is a finite number. You could use 8 product rules. The limit of a finite product is the finite product of the limits. And I can write this as n plus 1 over n times n plus 1 over n times n plus 1 over n times n plus 1 over n. Each one of them goes to 1. There's only 8 of them, so their product goes to 1. We could also use how else could we handle this product? No. I mean, you could use L'Hopital, but you'd have to expand things out to the 8th power. You could use L'Hopital. L'Hopital would work. You would have n to the 8 plus 8, n to the 7th plus da 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 da. And when you use L'Hopital, you would have n to the 8 over n to the 8. What else could we use to handle this product?
Logs.
Logs! And in fact, that would work if we didn't have an integer like 8, but had a general real number. If we had the square root of 18.3, something like that. So if we look at the limit as n goes to infinity of the log of n plus 1 over n to the 8, this is just going to be the limit as n goes to infinity of 8 times the log of n plus 1 over n. Well, what does n plus 1 over n go to? N plus 1 over n goes to 1. So the log of 1 goes to, so 8 times 0 goes to, so 0. So if the log goes to 0, then that means n plus 1 over n to the 8 has to go to 1. And so that this expression here is 1 over e is less than 1. And so it converges. But again, what you're seeing is there's many different ways of solving this problem. We can solve the problem by L'Hopital's rule. We could expand things out and pull out the n to the 8. There's lots of ways of doing this. So depending on the algebra, you have many choices. Okay. Any questions on how to do this using the ratio test? Okay. So now, in a shocker, we move on to the hoops test. And so I will keep the phrase limit as n goes to infinity to save some chalk. I will have to change ratio to root. And I can change root a to an O without too much trouble. Put in another O. All right, so we want to look at the root test. So we want the limit as n goes to infinity of an to 1 over n. So this is the same as the limit as n goes to infinity of n to the 8 over n e to the negative n over n. Does this look familiar? This would not look familiar in section 1, but we did something a little bit different in section 2. Where have we seen this before? Yeah, you asked about this using the comparison test, right? So there's many ways to get to the same algebra. This is now just giving us the limit as n goes to infinity of n to the 8 over n e to the negative 1. All right, so that's 1 over e limit n goes to infinity of n to the 8 over n. If we happen to know that that limit is 1, we're done. We really just need to understand n to the 1 over n. To get some feeling as to what's going on, let's take a good number n and just try to see what happens. So we want to look at n to the 1 over n. If I look at 1024, that's 2 to the 10. Right? So 1024 to the 1/2, that's 2 to the 5th is 32. 1024 to the 1/10 is 2. 1024 to the 1/20th is the square root of 2. We're trying to get up to 1024 to the 1 over 1024. Already at 1 over 20th, we're already at the square root of 2. You can hopefully see that when you're taking this really, really high root, it's crashing the number towards 1. I mean, this is not a proof that it goes to 1, but it's at least giving you some evidence. So we want to calculate the limit as n goes to infinity of n to the 1 over n. How could we study this? So how could we study the limit of n to the 1 over n? Logarithms. When in doubt, take logarithms. So if we look at the limit as n goes to infinity of the log, let's do n to the 8 over n. We can do the more general case. This is going to just be the limit as n goes to infinity, the log of n times 8 divided by n. Well, what do we know about the log of n over n? Yeah, the log of n over n goes to 0 very rapidly. If you take n equals e to the 100, you have 800 divided by e to the 100. So this is just going to go to 0. So since that goes to 0, this means n to the 8 over n has to go to 1. And therefore, this is just 1 over e is less than 1, so it converges again. Any questions on the convergence here? So now we have to do the integral test. And there's a lot of ways you can do the integral test. So in section 1, I tried to break up the integral dyadically, which we had done for 1 over n squared, and it ended up leading to a more painful calculation. So I'm not going to go through and do that here. I will just say that if you want to, you can look at the section 1 video, which has the painful dyadic. If we're going to do the integral test, we need to think of a good function to use. Any thoughts as to what f of x should be? Yep, x to the 8, e to the negative x. And so we would want to integrate from, say, 1 to infinity, x to the 8, e to the negative x dx. Any thoughts on how to do this? Yes, how many times? 8. It turns out that there's actually a faster way to do this. It's a beautiful method called differentiating identities, which I cover in probability, that you can convert this to a purely algebra problem. But as this is given, this is going to be painful. So it's going to take 8 integration by parts. Is it doable? Yeah. If your life depended on it, you could do it. And you only have to do it well enough to know, does this integral converge or diverge? So you don't have to do it perfectly. So when you're doing the integration by parts, all the boundary terms at 1 aren't going to matter, because it's just going to be a finite number. All the boundary terms at infinity won't matter, because you'll always have exponential depth killing the polynomial as well. So when you do the integration by parts, there's going to be lots of things you can keep throwing away. And you only have to do it well enough to show that it converges. So it's not terrible. It's not pleasant, it's time consuming, but it's not terrible. We can, however, say that this is less equal to, from some point onward, some big N, the integral from n to infinity, e to the x halves e to the negative x dx. So I'm using x to the 8 is less equal to e to the x halves if x is large. So I just need to show that this integral is finite. If I can show a larger integral is finite, then my original integral is finite. So when you're doing the integral test, you don't have to show that the integral you're looking at, you don't have to compute that, it's just show it's finite.
How do you know that x to the 8th is less than e to the x over to the x?
Experience. So this is similar to what we've done before. So I know e to the x halves is equal to the sum and goes from 0 to infinity of x halves to the n over n factorial. If I take the term n equals 9, this would be greater than x halves to the 9 over 9 factorial, which is x divided by 2 to the 9th times 9 factorial times x to the 8th. Once x is larger than 2 to the 9 times n factorial, this thing here is going to be strictly larger than x to the 8th. So this is going to be greater than x to the 8th if x is greater than or equal to 2 to the 9 times 9 factorial. So that gives me my sufficiently large n such that x to the 8 is less than or equal to e to the x halves. So what we're always doing is we're looking at the expansion of e to the x, and we're just focusing on just one term. And so if I drop everything but one term, I've made it small. Here's my x to the 8, and that x over here can overcome the 2 to the 9th 9 factorial if I go sufficiently far down. So once x is at least 2 to the 9th times 9 factorial, this is going to be strictly larger than x to the 8. And now when I have that, this integral over here is going to be equal to the integral from n to infinity of e to the negative x half dx. And I'll leave that for you to integrate use substitution and show that that's finite. And so what's nice is at the end of the day, I haven't actually calculated the integral that we're supposed to calculate, because I don't have to. The goal is not to find the value of this if I want to determine if the sum converges or diverges, but to just determine is the sum finite or infinite. Yes?
Would we ask find what a sum converges to?
So I might ask you to find what the sum converges to. I might ask you to approximate the sum. And so it's very hard to calculate the sum exactly, but I might say approximate the sum. And if I wanted to approximate the sum, then I would have to evaluate the integral.
And would that then be an approximation, or would we have to add something?
That would be an approximation, and we covered in class that you're basically missing the first and the last terms.
So would we have to say like this is an approximation?
Right, is that the sum is strictly greater than this integral and strictly less than this integral plus a1. It's an extra term like that. And so if you want to calculate something close, then you can't do all these approximations. If you want to just find out what is the actual value, then we have to do a lot of work. But if you want something weaker, if you want to know just does it converge, if you want to know approximately what the sum is, then just integrating from 1 to infinity will be a pretty good approximation. But I might want to know how much am I off on? What is the first thing you do when you enter an elevator?
Check the weight.
You check the weight, right? And then you look around and see who else is in the elevator with you. How accurate do you think it is when they say 2,000 pounds?
I hope they give a little bit.
So you hope they give a little bit of a leeway, right? That it's not going to completely destroy at 2,001 pounds. how much leeway do they give? That's an interesting question. For elevators, usually they're small enough that you don't really have to worry about that many people coming in and turning the weight limit. Sometimes on bridges, they are concerned about how much traffic is going over the bridge at certain times of day, especially if there's construction going on and they leave equipment on the bridge. And so when you're doing a lot of these things, frequently it's enough to just have a rough approximation of what is the sun equal to. But sometimes you actually want to have exact tolerances. I want to know upper and lower bounds. And the integral test can be made exact, and it can give you upper and lower bounds, so that when you estimate the sum, you can say, not only is this the value of the sum, but I know I'm not off by more than this. If we have an alternating series where the terms alternate, positive, negative, and their absolute value is getting smaller and smaller and smaller, this is great. If we've just added a positive term, that's a new upper bound. And then when we subtract a negative term, that's a new lower bound. Then when we add the next positive term, it's going to be smaller. It's a new upper bound, a smaller upper bound. And so by just, depending on, do you cut yourself off at a positive or negative term, you now know if you have an upper or lower bound. So if you just take two of them, you now have a little window. Any other questions on sequences and series? So the hardest part is knowing what to look at. And the best way to know what to look at is to just do lots and lots of problems. The more problems you do, the easier it's going to be to see what you should study. All right. So on Wednesday, we will do your Green's theorem in a day. This is something that if you're going to continue in physics or maybe chemistry, it's something you really need to see. In pure mathematics, it occurs in many different areas. I don't want to start Green's theorem with 10 minutes left. And so what I will do instead is I will share one of the most beautiful ideas I've seen in all my years in school. It's a beautiful idea from physics, from special relativity. And I'm sharing it because the theme of all of these is that a lot of times it's purely mechanical. Ratio test, root test, purely mechanical. Comparison test, it's looking at things the right way. And the more clever times you see of looking at things the right way, the better. So my physics textbook in high school had a amusing quote which has stuck with me all these years later. It's trying to describe some of the surprising results in special relativity, where you're traveling at very high speeds, close to the speed of light, and strange things happen. Your time slows down, your length contracts perpendicular to motion, mass seems to change. Very surprising things. If you're on a train that's traveling at 100 miles an hour, and you're running on the train in the same direction as the train at 10 miles an hour, how fast does somebody on the platform see you moving? The train's going 100, and you're on the train going 10. Excellent, about 110. People used to say 110. You've got to be very careful. We can't prove things, we can disprove things. What you can say is, it seems like speed is additive when speeds are small relative to the speed of light. It looks like you just add the speeds, and we can't tell the difference between 110 miles per hour and what you're actually doing. Or at least we can't until we have really precise measurements. 100 years ago, they would not see the difference. The quote in my physics textbook was, these results seem surprising, but you have to remember, most people don't have experience traveling at 3/4 the speed of light. I like the use of the word most people, and the phrase most people. So one of the surprising facts in special relativity is that length contracts perpendicular to motion. So if this is traveling at 3/4 the speed of light, it's going to look short to somebody standing still on the platform. But length does not contract perpendicular to motion. And the following is a truly beautiful thought experiment. So imagine you have train tracks and you have a train. And the train is traveling at 3/4 the speed of light. Have any of you seen Back to the Future 3? Excellent. All right, so this is the train from Back to the Future 3 at the very end that can fly. Because, of course, if it's no longer on the wheels, a normal train would have issues. So imagine you have two cans of paint at the bottom of the train. And so if the train is stationary, the paint lands on the rails. Okay? Now the train is traveling at 3/4 the speed of light. Imagine length contracts perpendicular to motion. So somebody on the ground, they see the train contract. So on the ground, it would look like this. Where does the paint land? Inside the train tracks, outside, or on? So somebody on the ground.
But wouldn't it only contract this way? So it would select on?
Well, no, the train is traveling in the horizontal direction. Let's assume length contracts perpendicular to motion. So length contracts in the y direction. So the train now gets a little thinner. So would it look like the paint is landing inside the train tracks, on the train tracks? It would look like it's landing inside. Right? So somebody on the ground would see the paint landing inside the train tracks. They used trains because, in the early 1900s, the train was the fastest mode of travel. And nowadays, we would use a walk. What if you're on the train? If you're on the train, does it feel like you're moving? No, it looks like the ground is moving. And so you would see the train tracks contract if you're on the train. And so the train tracks would now be inside. Where would you see the paint land if you're on the train? Outside the train tracks. And so what you can do is the train goes on for some distance and the train slows down and stops and you get out. Now, the paint should not suddenly move from being inside to outside because you've slowed down the train. You've got to be able to see the same physics. So different observers under special conditions should be able to see the same, should see the same physical reality. Could there be contraction perpendicular to motion? No. No. Could there be contraction parallel to motion? Yes. This says nothing about what's going on parallel to motion, because then the paint would land on the train tracks. And you wouldn't be able to tell any difference. But this simple thought experiment shows that you cannot have contraction perpendicular to motion. Absolutely brilliant idea. So you're assuming physics is such that different observers will observe the same thing. One of the consequences you get is that you can't have contraction perpendicular to motion. It is really hard to see something like this. Nowadays, you can argue about who gets some of the Nobel Prizes. It's become a little bit political. When Einstein got the Nobel Prize, he did not get it for special relativity. There was still thought that special relativity wasn't going to be quite right. But even if he was a little bit wrong with special relativity, he'd done so much great stuff. Other than special relativity, he still merited the Nobel Prize. He had 6 monumental papers in 1905. Does anybody remember any of the other papers? There was one on Browning in motion, and there was one on the photoelectric effect and the photons and stuff like that. We had, I think, 6 papers. Anybody remember what Einstein's job was in 1905?
Maybe like a high school or something.
Not quite high school. He was working in a patent office.
Oh, okay. Yeah.
And so one of the big issues we have now is when you have people submitting their work, do you treat the work seriously? Do you treat it as a serious submission? It's so easy to be dismissive. Oh, this is just coming from a high school teacher, a patent clerk, or whatnot. Is how much time do you give to some submissions like this? And there are lots of stories of great ideas that have been buried and lost for long periods of time. The problem is most of the submissions are garbage. And occasionally there are nuggets. Ramanujan, if you know the story of Ramanujan, is another one where Hardy, one of the greatest, analysts of the century, got the submission from Ramanujan and at first was not quite sure what to do with it. The formulas were so strange. It was like, you'd have to be a madman to write down formulas like this. Hardy started trying to prove them and realized that there was something here. Ramanujan had sent his work to someone else before Hardy, who just threw it in the trash. Because you get so many submissions like that. And so I like to take the opportunity to just warn everyone that take the time when people give you something. You might have to tell them, hey, please, before I look at this carefully, I need you to rewrite this in a way that's readable. You know, I just got a manuscript where it was a stream of consciousness. You know, all the math was in essentially one paragraph. It was like Joyce's Ulysses. And you know, I said to the author, I can't read this. So you know, please try to write this in such a way that it can be followed. But you know, the lesson here is to just really think about, you know, can something be true, and to really look at it objectively and not take into account the source. Here, absolutely brilliant idea, thought experiment. When you're doing the comparison test, a lot of times the comparison test is going to be very straightforward as to what to compare to. But sometimes you're going to need an incredible insight like this of what should I look at. And so you got a nice one today. Was, well, what if I just write n to the 8 in another way? Let's try to make it a little bit nicer. Okay. Could this help me? All right, this is a good place to stop. And then we will do Green's theorem on